Okay, welcome to the second part. We continue with the buoyant force, which held the objects to float on the water. In the previous part, of course, we found the ratio between the volume of the iceberg, the upper portion of the iceberg, divided by the displaced volume. No? With this, of course, after replacing all the results, we can, but you can see that what you need is the density of the water and density of ice right now. And actually, the problem of the iceberg, for example, can be found here. Look at here. Can you copy this formula? Let's copy this formula separately here. Let's put it here. Du, the displaced, water, ice, -1. And let me delete this part for clarity. It's a simple analysis of forces. And you will find problems like this. For example, an iceberg having certain volume floats in the seawater. They give you the density of the seawater. Density of seawater is 1.03 grams divided centimeters cubic. You can compare in kilograms per cubic meter. That's not an issue. And they say a portion of 224 centimeters is above the surface. So BU. This is the portion over the surface. Then calculate the density of the ice. And the total volume of the iceberg is given by this. Actually, this number here doesn't appear clear. But let's see below. They wrote it better. The information of this problem is density of the water. Volume of the iceberg is 2060. Volume of the seawater about the surface of volume. Well, this is I think it's the volume of the iceberg over the seawater. I think this translation is wrong. Density of the ice is what you will find. Volume of the water display, blah blah blah. This kind of information you can find yourself, but the equation will be the same. You have again mass of the iceberg times gravity equal the weight of the displaced fluid, which is the density of the water, seawater, displaced volume, gravity, and the mass of the ice is density of the ice times the total volume of the ice is equal density of the water, displaced volume. Then, of course, the ratio, here they are asking you the density of the ice. No? So density of the ice should be density of water, displaced volume, divided volume of the ice. And that's it. And then you play with those variables. I think we shouldn't go into the numbers so much because anyway, it's just replacing and using calculator and doing the conversions. And I will just send you sample problems anyway. Because for not consuming so much time. But here, I would like you to do this exercise. I would like you to replace the density of the seawater here and the density of the ice here. The density of the ice you can find in the internet actually, more or less 0.91. You can convert it. I will let that as a homework for you, and then you will tell me the portion of icebergs immersed in the water. In the exam, we will include this. No, the exam is until when? Until. No, what I mean, the topic is include thermodynamics. No, fluids. No, this part no, probably. So this part is for the final exam. No. So please replace that information. Find in internet density of water, density of ice. Also, I will send you this problem for you to analyze it. It's done already. Actually, they did it here. they found the density of the water to be like this. And look the analysis they did. Let's take a look a little bit to the analysis. Weight of the iceberg is equal to the weight of water displaced, which is what we have been doing the whole time here. So it means volume, rho 1 is the density of the ice, rho 2 is density of water. Then you replace the corresponding values. And at the end, it comes out that the density of water is. What do you notice when you compare the density of the water and the density of ice? Which one has larger density? Yeah, the water, definitely. So obviously the ice will float. Yeah, that's the idea. So there is no mystery with this, I think. I think you should be able to do it. And that's not a problem. So now let's go to hydrostatic. Let's say when probably the next class I will start asking you what was the result you obtained from the amount of volume immersed from an iceberg. Just take the information from the internet, density of seawater. I think the density, of course, changed with the temperature, but the change is not significant. It's not significant. Well, there might be changes in certain areas or regions of temperature, but I think if you have water at 50 degrees and water at 60 degrees, the difference in density it will not be so significant. No? So most likely you can take as a constant. The density of the ice is also a standard. We can search in the internet, and then please try to calculate what is the percentage of iceberg below the water. Now let's go to hydrostatic. Hydrostatic is something very important because it's related actually with what we were talking about buoyant force. Remember, the buoyant force is a consequence of the difference in pressure between the two levels. No, if I have an object here, look at this time. Let's call this point 1, and let's call this level 2, and let's call this level 3. 1, 2, 3. And this level is at the same level of this hole. This is at the same level of this hole. Then which level has larger pressure between 1, 2, or 3? 3, exactly. Why? Because it's deeper. This has lower. Why is the pressure here in the surface? The atmosphere, one atmosphere of pressure. The atmospheric pressure, unless you put air with very high pressure here, or if you decrease the pressure of the air, what will happen? If you extract air from here and reduce the pressure, this will start to evaporate. The water will start to evaporate. But let's forget that situation. Let's assume that it's atmospheric pressure. And then what you will have that the deeper you go, the larger the pressure is. Then this water here will escape in a parabolic motion because each particle obeys the parabolic motion here. This thing. There are ways, we will not do that calculation, but there are ways to calculate the distance. It's a standard. And if the reduction of the level of the tank is very slow compared with the velocity of this of the water going out from the holes, then we can apply hydrostatic approximately. This happens when the tank is very big. You have a very big tank, and these holes are small. The water is escaping, but you see the tank. Even if the water is escaping, still approximately, the water is not moving. Let's say it's reducing the level too slow, then hydrostatic can be applied there. In here, if the tank is big enough, you can apply hydrostatic. You can do it. But here, you cannot apply hydrostatic. Here is where Bernoulli appears. This is where Bernoulli appears because you have kinetic energy for the flow of water. You have the potential energy for the difference of levels. And you have, of course, the energy to pressure. Of course, here the pressure is atmospheric. So, okay. So normally, let's put that the depth of this is 1 meter, 2 meters, and here is 3 meters. 1, 2, 3. Then you should be able to calculate the pressure right now here. The difference of pressure with respect to the atmospheric pressure is called manometric pressure. Normally, the pressures we calculate are manometric. So let's try to do it like that. Calculate the pressure 1. So the pressure is the density of the water, gravity, and depth. Rho GH. And you can see H is the depth, G is gravity, and rho is the density of the fluid. Where is pointing that pressure? What is the direction of that pressure? Any idea? Remember, when the fluid is static, it has to be in equilibrium, ideally. So let's analyze one point. Let's isolate one point of the water in this tank. I take the point here, this point. And the water is static. Then what is the direction of the pressure felt by that point? I explained that the last time, you remember? Somebody can remember? The direction of pressure. When you are inside the water and there is a huge pressure of you because you have this column of water over you, which gives you a huge weight, it's huge weight over you. What is the direction of that pressure? Ego. Any idea? What about you? Hello. Any idea? Is the same in all the directions. Let's say it's pointing. This point, let's isolate this point. Let's go assume here. The point is here. Since the point, ideally, this portion of water, which is a point, of course, a point containing many atoms of water, many molecules of water, no atoms, molecules of water. Therefore, it not to move, it has to be in equilibrium. For being in equilibrium, it has to be a pressure down, well, the same pressure up, the same pressure left, the same right, the same in any angle. So at the end, each point has a multiplicity of pressures pointing toward it. This is the danger of being in water, actually. You put a tank, imagine you have the submarines. Let's talk about the submarine. Do you remember the accident of what was the name of this submarine which imploded? It suffered implosion. It was a tourist submarine. Very small, very comfortable. I'm wondering how can the millionaire people pay so much for such a risky thing? I mean, they have a lot of money, and instead of using it in a very useful way, they go, oh no, I want to see the Titanic below, which is a bunch of metals already. Who cares? I mean, many people die before. Yeah, we feel sad about that. And I am sure they are not sad about that. They are going to see it because they want to take pictures. Then the submarine implode. You remember? No explode, implode. And implode is because the pressure may collapse. The pressure was so huge that I don't know, probably what they found, it cannot be considered a human body. It should be something, maybe a microscopic bodies. The bodies became very small, probably. Like, this is the person. This is the other, this is probably. And then why are we talking about that? Because the submarines, they have to be designed to resist huge pressures below the ocean. That's why you see the design of the submarine, not only aerodynamic. Well, aerodynamic is not correct the word, no, because aerodynamic is for the air. But the fluid dynamics, let's say, the dynamics, the dynamical design has perfect for moving with a small resistance to the water, because it has friction due to the water when they move. but also the resistance to the contraction has to be huge. The planes are the opposite. We were talking about the planes the last time. You remember when the plane take off and you are 20,000 feet over the level of the ocean, or 40,000 feet. I know more or less the numbers because I check the map when I am traveling. I always check the map. 800 kilometers per hour usually, and 40,000 feet. We will use those numbers for some problems later. What happened with the plane? The plane has to do the opposite. It has to survive high pressure inside because we have to pressurize the cabin and low pressure outside. So the tendency of the plane is to expand. The tendency of the submarine is to collapse a little bit. And it's important to avoid concentrations. For example, you can see the submarine without not so many sharp portions, because the sharp portions are concentrations of efforts, and is where the materials fail. The materials fail in those points, which are sharp. Then they try to avoid that. So coming back to the topic, if you have a submarine, go down, you have to design correctly with the appropriate materials. These guys, they designed it with a very crappy material. It was a crappy thing. They say, let's make this company with cheap materials, some materials which nobody has tested. I mean, they were the testers. I mean, these guys were the Guinea pigs. The tourists were the Guinea pigs. And they were paying this company for growing, no? And it's very unfortunate that this happened, but it's very big irresponsibility from the company. In any case, let's calculate the pressure in 3, the pressure in 2, and the pressure in 1 based on this symbol, and let's assume that the fluid is water. Let's take the density of water. Can you tell me the density of water? For not making mistake, let's put it here. 0.3. Let's project it here, like this. 1,000 more or less. It's 1,000. Let's put, then the pressure at each point will be 1,000 kilograms cubic meter, multiply the gravity, let's take gravity like 10 meters second square, and let's put h for the moment. And of course, h will be 1 or 2 or 3 meters. Then you should be able to calculate this part. This is the formula we are using here precisely. So what is the result for 1 meter? Is only 10,000 pascals. Pascal, which is Newton divided meter square, if you put everything in the units. Of course, for 2 meters will be 20,000 pascals, and for 3 meters will be 30,000 pascals. So the result is 10,000, 20,000, 30,000 here. You can see how the difference in pressure change. And you will see later that hydrostatic is a special case of Bernoulli. Because anyway, hydrostatic, as the name suggests, the water is not moving. So there is no kinetic energy. So you don't consider the kinetic energy. And there is no what? The other energy we are considering. The potential, the pressure, all these kind of things we are considering. Okay? So it's a special case of Bernoulli, and you will see that in a moment. So with this pressure, if I go here, let's assume that I select this point, the point 1. I know the pressure 1, and I want to go here and see at which velocity the water escapes the hole there. Then I apply Bernoulli. And Bernoulli is telling here that these 2 points are at the same level. So there is no difference in the potential energy they feel. The difference will be the pressure. In the pressure. Now, of course, pressure here we calculated. The pressure here is atmospheric. Since we are calculating manometric pressure, we take 0. The manometric pressure is the difference with respect to the atmospheric pressure. And we have zero velocity here and velocity here. Then kinetic energy. We will see that in a moment because I have not introduced Bernoulli. Then it's better to introduce Bernoulli before doing this kind of calculation. No? So I hope hydrostatic is clear. You know? Buoyant force is clear. It's clear why the objects can float in the ocean. It's a matter of the ratio between densities, the density of the fluid versus the density of the object. The humans, we can float in the water, for sure. We are filled of air and so on. And if we fill our lungs with air, is even better. The ships can float, even if the iron has higher density than the water, because they can be designed with cameras which are full of air, etc. And of course, if you throw a coin and an iron, it will sink because the density is larger than the density of the water. Well, if you go to that sea, which is full of salty water, I was checking that we were recording. I forgot we were recording. In that case, the density of the water is even larger, and you can float even easier than it. But I don't know how healthy it is to be in that water exposed, because the salts make you lose water, no, in your body. Actually, you shouldn't drink water of the ocean. Never drink water of the ocean. It will produce the opposite effect you want to achieve, no? Which is hydration of yourself. Hydrate, I don't know how to say, hidratar, huh? Hydration. Dehydration of yourself. But instead of that, you will lose water, for sure. Hydration. I seldom use that word. That's why I had to ask the
Portuguese, it's the same.
hidratación. Hidratación, sí, sí. Estamos como una mezcla de lenguajes, de lenguas, ¿no? Entonces está un poquillo confundidos acá. Okay, so I will put you a problem for you to do it later. Well, I don't think you are concerned about the demonstration of this formula, but this can be calculated easily. It's just to put a column of water, and the column of water has a force here, and this has a force here, and there is a pressure. The pressure is the force divided that area. Okay, and of course, when you calculate that, you should be able to reach this part. It's an equilibrium of forces. The difference between this and this is for the difference in levels, etc., and you achieve this. This demonstration I can send to you if you are interested, but here is not necessary. I think conceptually is what you concepts is what you really care about, no? So for the moment, it's okay. Now is the time of Bernoulli. Let's find here Bernoulli. Bernoulli's principle is here. Well, before going to Bernoulli's Bernoulli principle, I want to ask you, because I am sure you have experienced this in your life. I will ask you a few questions. In your daily life, you should have suffered this. You go to some areas where suddenly the air starts to flow fast, much faster than in other areas. In Tokyo, I remember I was living in an area called Sumida, very beautiful. A sky tree was there. Asakusa is near. You can cross the bridge. It's peaceful, etc. And then I remember there was a shopping mall called Olinas, and every time we cross a gap, the air was, in summer, was the best place to stay. You cross that, it was like, oh, like air conditioner, receiving air conditioner by free. And why is that? Why do you think it happens? The pressure, what happened with the pressure in that area? It's low pressure. It's an area of low pressure. The air is like the water. The water flows from high to low pressure. The air is not different. Now, let's do an experiment in your houses. Open a window in your room. One window only. What happened? Nothing. Now, open another window distant away. What would you feel? A lot of air entering because the air will start to enter in one window and going out to the next. You have decreased the pressure of the room, and the air increased the kinetic energy. It's a exchange of energies. The energy of pressure decreased, the kinetic energy increased. And the potential energy plays some role, but of course, the windows are approximately at the same level. So the potential energy doesn't play any role. When the planes are flying, they have to reach a speed, more or less 800 kilometers per hour. If the planes fly too fast, they will destroy their engine also. It's not so good. If they fly too slow, they will fall. They need some velocity, no? The cruise velocity is more or less 800 kilometers per hour. The wind, let's assume this is the wind of the plane. So the air in the upper flow faster or slower than the air in the lower of the wing. Obviously, the air on the top has to flow faster than the air at the bottom. Ideally, the wind, the design, the aerodynamic design is such that the air collides the wind below. It doesn't move so fast below. It creates a pressure upper. There is also a pressure lower here, but smaller because since the air flow faster here, of course, there is more kinetic energy than energy of pressure. Then the difference in pressure is pointing upward. I don't know if in this class we'll be able to do, or we can calculate actually. We can just find in Google the weight of a plane. We need to know the weight of a plane, the mass of the plane. We need to know the area of the wings, the area for knowing the pressure. We make equilibrium of forces to know what is the speed necessary for the plane to fly. I could ask you in the exam, for example, can this plane fly with this speed? And you should be able to tell me yes or no because of something. So this is the kind of problems we can solve, no, with this physics, Bernoulli. So welcome to Bernoulli. I talk too much, but I have not introduced Bernoulli formally. Look at this. This is like a water supply, any water supply anywhere. What do you perceive here? There's a pressure here. There's also a pressure in this side. They are fighting each other, this pressure fight. There is a difference in level. So this has more potential energy than this. The water located here has higher potential energy. About the kinetic energy, well, it depends, no? But the issue is that Bernoulli accounts all these things in a simple equation, which, let me see, the equation in the best form is this one. Maybe I should amplify this, no? Let me put it bigger. Zoom. This one can be seen, no? Now it can be seen. I don't know how to cross this part. Well, this is more or less Bernoulli. It's incomplete here, but I think it's good enough. This equation, how they portray it. You have pressure here. Sometimes people express it differently. There are different ways to, because sometimes the pressure appears divided with something. But you have pressure. This is the kinetic contribution, 1/2 density velocity squared. And this is the potential contribution, rho GH. What happens if these two guys, or better, what happens if this guy die? You record hydrostatic. It's hydrostatic. It's hydrostatic. Perfect. Excellent. Now, there is a mixterm here, which is plus rho g h. One, let's call to, or two. Let's call this two. And this, let's call one to this. Yeah, like that. So this is Bernoulli. In this case, they wrote in this way, probably they are solving one problem. And then, of course, we can proceed to solve problems. But let's analyze the meaning of each term. Each term, what does it mean? Evidently, this is pressure. This is the kinetic. This is and this is superposition is constant. So it means if I increase the pressure, I reduce the kinetic energy, which is what happened with the planes. Or vice versa. If I increase the kinetic energy, I reduce the pressure. And this is how the aerodynamics is designed. Now, what happens when the plane lands? That's when the plane takes off, and for keeping itself when take off, the wings are configured such that the velocity below the wing is almost zero, and it's very high on the upper, and then boom, you turbulence is scary, it's a little scary sometimes. And then when you cross the clouds, is the worst turbulence is when you cross clouds, no? That is where the plane really jump. And then you are on the top, normal. Now you are not ascending anymore. So the winds change a little bit. Now the velocity below still is lower than the upper part of the wind, but not as slow as before, no? Because you have to just to keep the height. Then after you are going to land, you go down. What happens when the plane touches? Somebody has, you pay attention to the wings. What happened with the wings when they land? They do. Why they do that? Because they are crazy? No, they are not crazy. What do you think is that? What's the reason? The reason is that now there is an inversion of the modes. Now it's like if the wind were operating in the opposite direction, like a Formula One race car, basically, it's putting you down. It's down. It's making you heavier for you to stop, helping you to stop more. And then what is the relation between the velocity upper and lower now? Now lower, the air flow faster, and upper, the air flow slower. And that creates the gradient of pressure down. And never remove the seat belt until the plane completely stops. What's the reason? We have a huge mass, it's tons and tons, it's a huge inertia, it's a huge momentum. Any small collision will send you to the pilot, basically. You will finish in the cabin of the pilot. So, well, I saw many people, unfortunately, mostly happen in China, unfortunately. It's like the plane line and some people immediately start, the flight attendants have to tell them, hey, sit. I mean, come on. So wait, even when the plane is slow, don't challenge that, because when the plane is slow, you can perceive it's slow, but it's a huge momentum. It's a huge momentum. Remember what the physics we saw before at the beginning of calculate the momentum of the plane, mass of the plane times the velocity. It's a monumentally huge. It's equivalent to you running probably 100 kilometers per hour or more. Put it in that way. I mean, think in that way. Then it's part of the education implies. Coming back to Bernoulli, let's come back to Bernoulli, is conservation of energy. Bernoulli is nothing else than conservation of energy, but written in a different way. It's written in a different way. Let's analyze this situation here. You have a point A and B, sorry, A2 and A1, AB, A2 and A1. And I want to calculate the pressures. Which point has larger pressure? A2. Which point has larger velocity, maybe? Well, this is narrow. Of course, the tendency is the water to flow in this direction. And then you will say, what you say that the water flows from high to low pressure. So is this challenging what we said before, or what is happening? Well, first you have to calculate the pressure here. From here to here, hydrostatic. And then, of course, here there is a pressure intermediate. And that pressure, of course, has to be larger than the pressure here. Certainly. This is where we apply Bernoulli. Okay? Excellent, excellent. Here. What about here? When the water flows from B1 to B, from this point A1 to A2, what happens? There is an expansion. The velocity what? Is lower here. And what does it mean? The pressure increases. Yeah, exactly. That's what happened. Of course, that's why it becomes lower. When I try to cover the water supply like this and make what I am doing when I am covering the water like this, I decrease the area. And then what does it have? The kinetic energy increase and reduce the pressure. Yeah, right. Excellent. So now we are ready to come back to this picture here. This picture here. And then we are ready to apply Bernoulli here. So well, let's copy the equation of Bernoulli because just for having it here. This is the equation. Let's copy it separately. Only one side. Let's put P1 plus 1/2 rho V1 squared plus rho G, the level. Let's call it C. This is a constant. It's a constant. This combination is constant. This is what Bernoulli found. And then let's apply that principle here. Let's come back to this point again. Let's put 3 meters here. 3 meters from the top to the bottom to here. This should be C over C here somehow. And then I want to calculate the velocity of a scale of this 0.3. The same apply for the velocity of a scale here and velocity of a scale here. Then what do you think you have to do? You have to combine your skills in hydrostatic and Bernoulli. We have to study both. We have to study hydrostatic, we have to study Bernoulli. Then what do you have to do first? We have 3 meters. And then any answers? The tank is big enough such that the level decreases very slow. This hole is very small, the water is escaping, but the tank is so big that the level of the water is decreasing slowly. So hydrostatic is approximately right in that case. Oh, sorry, I almost polite here. So the first thing is hydrostatic. Let's calculate the pressure here with hydrostatic. Here. Let's call to this pressure, not 3, I don't want to call it 3 because 3 is this point here. Then the pressure, let's put 3 prime. 3 prime. Is the density of the water, which is 1,000 kilograms meter cube, a cubic meter, sorry, metro cubic, cubic meter. Gravity, and the depth, which is 3 meters. So at the end is 1,000 cubic meter. Gravity, let's take 10 for simplicity. Meters second square. And this is 3 meters. And then This finished being what? 30,000. Is correct? Kilogram meter, Newton meter square is Pascal. Yeah, this is Pascal. So let's write in a notation 3 times 10 to the 4. 1, 2, 3, 4, right? 10 to the 4 Newton meter square. This is the pressure you find here. Now, for finding the velocity of a scale here, I have to apply Bernoulli. The energy here is equal to the energy here. But they are at the same level. 1 second, they are at the same level. What does it mean? That I don't care the height. So I ignore this term here. So let's apply Bernoulli here on the left first. Is there any kinetic energy? No. Is there any potential energy? No. Well, the difference there is, but respect to this point, but with respect to this point, no. Okay? With respect to the points at the same level, no. And then you only have pressure. So pressure in 3 prime is equal. Now go to the right-hand side in the point 3. The pressure is atmospheric. Let's take 0 because it's manometric pressure, what we care. The height is the same, so we don't consider it. And there is only kinetic energy. 1/2 density of water, velocity square. And actually, if we have not calculated here, the density is cancelled. Let's find the formula, the general formula first, and you will see. The pressure in 3 prime was rho G and the dip now. Let's put a C. And rho cancel. So at the end, the velocity is root square 2gc. Is familiar for you this formula? Do you remember that formula? When we solve problems of free fall with energy conservation, where you throw a body from certain height, and it falls. Or when you throw, when there's a parabolic motion also, is the same. And many other problems, no? And when we have these problems, like there was a body falling from here, there was a height, and then you will have to find the velocity here, and there was no friction. The same. Coincidence? No, there is no coincidence, because this is conservation of energy. Bernoulli is nothing else than conservation of energy applied to the fluids. That's it. But remarkably, these guys could do this in many years ago, no? Without having big experiments or so. So I think that's why we have to respect the scientists in the past, no? That's why Newton is over Einstein for sure. Much more, because was the guy who founded many things before, invented calculus, like Isaac, who didn't go anymore. And well, Newton calculus has some limitations. A parenthesis here is that there is a calculus called Ito calculus. It's used when you consider stochastic variables. It's used in problems of Brownian motion. There is perturbation theory, which Newton didn't consider either. No? Perturbation theory is very important also. Anyway, coming back to this problem, we didn't have to calculate this actually. All what we have to calculate, of course, knowing the pressure here is nice. Let's delete that. But all what we have to calculate is this. And at the end, the velocity, you can see, is independent, even about the density of the fluid. The density of the fluid doesn't influence. So you can put any fluid here, it will escape with the same velocity there. Is what this is telling me. Now, something important is, I will put an exercise just now. Let's invent something. Let's become a little bit crazy and invent things here. And let me delete this. What happens if I put let's put this, a tank in this way, but there is a hollow part like this. This is the same fluid. For simplicity, let's call it water. It could be water, oil, anything. Gas, gasoline, whatever. It doesn't matter. Some fluid filling this part. And this is air, I mean a hollow part. The pressure here in this point 1, you will have to believe me, is the same pressure here. Even if they are disconnected, they are completely disconnected, but the pressures are the same in hydrostatic. So at the same level, no matter if the portions of fluid are connected or disconnected, the pressure is the same. And this is very important for solving certain problems of engineering. In engineering. Another issue, you will investigate that one. You can transmit the force through the fluids. This is how the hydraulics, for example, when you move the planes, when they give an order in the cabin, the wing has to move, the plane has to turn the cars. When you move something, the wheels have to move. Or when you have to put the car up, when you want to change the wheel, all these things, most of these mechanisms have something in common. It's hydraulic, transmission of hydraulic forces. And this has application. The most immediate application is when you have, let's put this area, let's call it A2, let's call it A1. Let's put a car here, a truck, a giant car here. Then I apply a force here in that portion. Then when I input this force, that force is transmitted to the fluid and it can elevate this thing. And the idea is that I should apply a minimal effort for that. So I think the next class we will start with that, with these kind of problems. But I want you to investigate this mechanism, how it operates. So let's put investigate this kinds of mechanism. Of course, you have to apply the fact that there is a force, there is an area, of course, there is a pressure here. The pressure transmitted in the fluid and the elevator. Also, you have to take into account that the displacement, a huge displacement in this side is a small displacement here. Well, of course, the force you transmit here is much larger than the force you input here. And that's the idea of the hydraulic force, fuerza hidráulica, force hydráulica. In Portuguese, how do you say? Exactly the same. Well, the idea is to apply a small force and you can make a monumental motion. A small force, well, it has to make a long motion for creating such effect. We will start with a problem in next class about that. Now I will just propose for closing this session. Let's finish the issue of Bernoulli. Let's find the information of a plane. Or you prefer to solve this kind of problem, so we go to the plane directly. Okay, before going, I want to see how you are. Calculate, now that we know the formula for escaping the water here, evidently the water in the first hole will escape with root square 2g h1. The water in this hole will escape like root 2g h3, and this will escape v2 root square 2g h2. Then it's clear that the water at the bottom will escape with higher kinetic energy, the largest kinetic energy, largest velocity. And the reason is because the pressure which push that water outside is much larger. The pressure here is pushing the water to escape. The pressure here is pushing the water to escape, and the pressure here is pushing the water to escape. Look at the aquarium you have here. You have many aquariums here. You have many fishes, and those fishes that throw water from the mouth. If you make a hole, imagine you make a hole to the aquarium. The deeper the hole, the faster will be the velocity of escape of that water. And without any coincidence, it matches with the velocity of a particle falling, no? In free fall, or the velocity we calculate in those problems of conservation of energy, because this is nothing else than conservation of energy. Now let's formulate at least the problem of the plane flying. Let's find the information in the internet. Let's be a little bit dynamical. The weight of a plane, average weight of a plane. Let's put like this. Weight of a plane. Kilograms, because I don't like these pounds and these kind of things. I don't want to convert. Let's select 450,000 kilograms. The weight of a plane. Let's paint the plane here. I think I sent the solved problem. I was trying to, I sent a solved problem about the planes to the students last year, but I don't know where did I put it. I sent them by email so I can check it later. But let's put the mass of the plane. Let's put 45, 1, 2, 3, 4, 1, 2, 3, 4, times 10 to the 4 kilograms. For writing it short. Now let's find the area of the wings. Area of the wing of a plane. Well, the idea is the following. Well, there's no information immediate. Meter square. Okay, now we have Boeing. You can see the Boeing 7. I will make the zoom here. Let's make the zoom. Increase. There you are. We have to select one plane. Let's select one plane. Boeing. Of course, I hope the weight matches, but it doesn't match. It doesn't matter. The idea is to make the exercise. So Boeing 737, whatever, it has 91.04 meters square, the wing area. So there are two wings, no? There are two wings. So at the end, we multiply by 2. This Boeing 737 here has 124. Which one do you want to select? You select. I'll let you to select the area of the wings. Then let's paint the plane for the moment. The plane is this. I paint the plane here. Jam, 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 jam. This is the plane. Now, why I care so much the area of the wings? Because the wings, all the weight of the plane is over the wings, man. I mean, if a plane lost a wing, bye-bye. Bye-bye. See you in the next slide. Bye-bye. That's the end. Because the issue is like this. When the plane takes off and it's in the air, people don't know, not so many people, especially those who don't care physics, they don't know. But, you know, the wings is the most important because they sustain all the weight of the plane. So this union is very important between wing and, that's why it's very soft. You can see that the union is soft for avoiding concentration of efforts. If you do the union too sharp, there is a high concentration of efforts in the corner and it destroys the wing. It will make this point fragile. That's why it's soft. In addition, the wings have to be flexible for avoiding to be destroyed because they cannot be fragile. The material cannot be fragile. Fragility is not allowed at this level because our life is fundamental at that point. No? And we all need the planes. We all need to fly. The safety of the planes is very important. These kind of calculations, any engineering of aviation, they have to do it eventually. Then you're not engineering of aviation, but I mean, knowing these things, I mean, this is one of the most applicable things you will see in your life. And probably even for applying this, something as simple as a drone, maybe you're investigating something and you need to know which velocity some device should have, I don't know. And even when you are inside the water, if you have some engine moving inside the water because the water is a fluid, the air is a fluid also. The same principles apply, the same principle. Then, okay, let's select this one, 122.4 meters squared. Do you agree? This one. So this is an Airbus A321. Airbus A321. I don't know if we will have time, but at least we can formulate the problem, and you will see what we will do. We have the mass of the plane, so we know the weight. The number of people's baggage will add some weight, but I think most of the weight will come from the plane itself. I don't think the weight of people plus the baggage will add so much. Well, it adds some amount, but in order of magnitude, I think the main will come from the plane itself, and of course the fuel from you put the gasoline, which is normally kerosene, not very heavy. So we have this information. We have the areas of the wind, area 1, area 2. Then I want to tell you, okay, let's assume that when this plane is taking off, the wind configuration is such that the velocity, let's apply Bernoulli to the wind. Let's take the wind, the air, the plane is moving to this side. Let's take the 800 kilometers per hour, which is the cruise speed of a plane, more or less. 800 kilometers. During the takeoff, the plane doesn't have this speed actually. But of course, there is a limit after which the plane cannot come back. You know that when the pilot is taking off, accelerating, there is a limit after which they have to take off no matter what. And that's what happened to the accident of Concorde. They realized about the fire, but it was too late. They had to take off anyway. There was no choice. If they don't take off, they will die anyway because it's just going against a wall or something. Then the hope they have is to take off, come back, and land again. Unfortunately, the wing got destroyed. And because the wing got destroyed, there was no capability of sustaining that weight. Another important thing for the plane is the tail. The tail is like what tells if you go to the left or to the right. A plane cannot be controlled without the tail, but that's another story and I don't want to touch it right now. Then it's in 800 kilometers per hour and the air, let's assume that the air around is not moving, it's random, but in average it has zero velocity. In average, which never happened. No? There are currents of air, but let's assume because we are in the idealization. If this is moving forward 800 kilometers per hour, it means that the plane, let's say the upper part of the plane, the air is moving backwards at 800 kilometers per hour, ideally. And on the lower part is zero velocity approximately. Well, let's put it 40 kilometers, something. But let's put it zero just for calculation. Put it zero. Let's apply Bernoulli. Are you able to apply Bernoulli here? Do you remember the question of Bernoulli already? You forgot? We have it here. Pressure, time. Now let's analyze the energies here. There is evidently a difference in kinetic energy between the upper and lower part of the plane, or the wing of the plane. Is there any difference in the height? No, it's almost the same. It's a ridiculous a few centimeters, maybe. Maybe a ruler is no more than a meter, less than a meter. So it's ridiculously slow. Sorry, ridiculously long. So we will not consider that. We'll consider only. So this part we will not consider. We will only consider pressure and kinetic. Pressure and kinetic. So the pressure below, there's a pressure below. Let's call B from below, and there's a pressure pointing down from the bottom, from the upper part. Then PU. At the end, what the plane feels, the force, the net force, putting the plane up is PB minus PU multiplied by the area 2 times, because it's 2 areas. But we have to find this gradient of pressure, and this gradient of pressure is calculated from this equation. Then let's put here, upper part of the wing is the left-hand side. Let's call it upper 1/2 rho. Density of the air is the density of the air. Velocity upper squared is equal to the pressure at the bottom. And the velocity of the bottom, I neglect also. So it means that pressure of the bottom minus pressure upper is 1/2 density velocity upper squared. And this is what I have to replace here. It will be 1/2 and 1/2 cancel actually. Is 1/2 density velocity upper squared times the area. These two and these two cancel. And what remains? Density of the air. Density of air. Velocity upper, which is 800 kilometers per hour squared. The area, we say the area, it's in the other page, wait. The area of the plane, we put 122.4 meter square. And the density of the air is what? Let's find in nice units the density of the air. Density of air. Now the density of the air, of course, changes with the height, no? Is this 1.293? Then this will be 1.293 kilograms meter cubic, 800 kilometers per square. Now, if I want to, I have to convert these hours into seconds, because I need to take into account that. Then, of course, let's do that conversion immediately. Before putting the area here. Inside here, I put 1 hour is 3,600 seconds, right? I think it's like that. Square. Then 122.4 meters squared. And this force, in principle, should give you in newtons. If we verify all the units, at the end is Newton, which is kilograms, meters, second squared. You can verify that the units are consistent. Please verify. And then calculate this and tell me what is the force. If this force is larger than the weight of the plane, this can fly. If this force is lower than the weight of the plane, this cannot fly. That's it. And what's the weight of the plane? The weight of the plane is simply the mass of the plane, which is 45 times 34 kilograms times gravity. Let's take gravity like 10 meters second square. And this is equal to 45 times 10 to the 5 newtons. This is the weight. So let's verify that this force, the force which made the flight possible, is larger than the weight of the plane. And this, we have solved the problem of the plane already. This is all the calculation. And then, professor, what happened with the area between the wings. No, we don't care that because they don't contribute to the force. So, I mean, the whole weight is on the wings. Actually, the opposite. That's the area where we are, and we don't have so much. No, we don't have so much. Any questions so far here? It's clear, no? It's super clear. I mean, it's as clear as water. And this is Bernoulli, man. Magic. I mean, that Bernoulli. Imagine from Bernoulli, we can design planes. And the planes allow us to go to distances which before nobody could. The buoyant force allows us to construct ships. So basically, the hydraulic forces for transmitting forces to fluids, through fluids. Imagine all the industry, almost all the industry, practical industry. Well, quantum is also practical. Let's call a lot of industry is inside its physics. It's inside its physics. And then the question is physics useful? Do you find it useful? Of course it's useful. I mean, what's the name of the brothers who made this plane flight? Bright Brothers. Not the Green Brothers. The Green Brothers are the guys of the tails. Okay. The Wright brothers. I mean, when they did that small plane, which flew, I think, only 1 meter over the level of the ocean or so, and I don't even know if it collided or what happened with it, and the speed should be very small. I am sure they apply this. I mean, in the past, these guys who have money, it's not happening nowadays so much, but the guys who were millionaires, they were very smart. Nowadays, I have my doubts. At least they have a lot of people working for them, but I cannot guarantee they are smart. They can be just the face who portray the smart, but there are many smart people working behind. No? Then, please calculate this. Can you tell me what's the number? Actually, the class finished already. Sorry that it took a little bit longer. But then you calculate this. In the next class, we'll restart from this point. Do you agree? Then let's stop today. But now you know why the planes fly, why the ships can float, why you can swim. The fishes function is very important. What you learned today, you know hydrostatic. You know the relation between hydrostatic and Bernoulli. You know the buoyant force. You know how to calculate the percentage of iceberg inside the water. Next class, please. I want to start from that, and you will tell me what is that percentage. And you will also tell me what is the result of this force in next class. And we will start with those two problems. So thank you. Thanks for coming. See you. So I will stop this recording here.